induction. Please remember, we will discuss it. Second, polarization quickly. And then we are now discussing about third phenomenon, current. So distribution of current is characterized by vector current density, we know physical meaning, and it's related with electrical field in this way, Ohm's law. Conduction current proportion is equal conductivity times electrical field. Now, equation is extremely simple, awfully simple. Sometimes it creates confusion. Oh, it's so simple, no difference between current density and electrical field. Wrong. Completely two different fields. No common feature. One, force field. Force which acts on the charges. Another is a water movement. No, quantity which characterizes motion of the charges. But beautifully, they are related in very simple manner. Now, we spoke about conductivity. Conductivity, I told, is related with two quantities. Density of charges and mobility. For instance, there are two types of conductors. I only remind you, electronic conductor and electrolyte conductor, ionic conductor. In metals, these charges don't move. Positive charge is not movable. It's a corner of lattice of crystals. But main conductivity is defined by mobility and density of electrons. When we have our rocks, we have movement of two charges, cations and anions, which are moving along poles. Now, two types of conductivity. Before I return back to formation, let me tell you about mobility. If I ask you a question, wire, piece of wire, quickly electrons are moving or slowly? Question is clear? Oh, I will look at that. Yes. Huh? Sorry? What does it mean quickly? But for example, you have piece circuit.
I think so.
Huh?
No,
yes. So we are going to casino in Nevada. Yes, a little bit slowly or quickly. What our knowledge tells about velocity of, because mobility is a quantity which characterizes velocity of electrons. For example, velocity equal plus minus mobility times electrical field. So for positive charges, if it's a positive charge, then it's a plus. Velocity, particles is moving in the same direction as field. Negative, minus, clear. So mobility is the quantity which characterizes how quickly our electrons are moving. So I have a question. Again, I have a wire, I took battery, there is a current, 1 ampere. My question, how quickly electrons inside are moving? What is their velocity? It's the same question about pore, ions inside of pores. How slow? So I specially brought to your attention this question. If you really would like to understand our method, it's not too bad to ask yourself deeper. Current, motion, we measure it. Ions moving, electrons are moving. It's not too bad to understand how quickly. Maybe they are lazy, maybe they almost don't move. Maybe the speed with light they are moving. Who knows? It's not too bad for geophysicists do know. Oh, that's better. So amazing fact. It looks like they are very quickly moving, vice versa. They are moving extremely small, taking into account magnitude of our electrical field. They move velocity, W, move extremely slow. 10 minus 5, 10 minus 5, 10 minus 6 meter per second. Imagine these lazy electrons are able to create strong magnetic field. We will speak a little later. But they almost don't move. But 10 minus 5, 10 minus 6 meter per second. Electrons. If you ask how quickly ions are moving, it's very easily from common sense to realize even much slower. So that's what I wanted to tell you. I expect from you question. I do expect from you question. In Sydney, there is a power station which generates field, current. Maybe there is no in Sydney, but let us assume there is a power station. Then there is a transmission line to Perth. 3,000 kilometers, it's enough? 3,000 kilometers, it's enough. Thank you. Then load, for example, balls, right? Load. You turn off generator 8 o'clock morning in Sydney. Then you start to observe effect in the Perth. Huh? Sorry? So that's transmission line which we all of us see. Why? Correct? That's grounding. Forget about it. So my question is, no current, no more divergence. We are approaching to our electrical methods. So my question is, 8 o'clock I turn on generator power station. When we start to see 8 o'clock. Strange. On one hand, velocity 10 minus 5 meter per second. How long it takes to reach 3,000 kilometers for electrons? You understand? So take 3,000 kilometers, transform into meters, 310.6, then divide by 10 minus 6, and you would be in trouble. Your, my, and all of us life will not be enough. So, maybe I will answer the question when we start to consider electromagnetic field. If I don't answer, remind me, please. If you can, maybe you are already ready to answer. Where is the paradox? Always means we don't understand something.
I don't understand that they move at 10 to the minus
6. No, but we have to accept it. There is no way because it's experiment and theory shows it. I'm ready. Sorry?
But then they still have to be moving at the speed of just that short.
10 minus 6 meters per second. If they even suppose they pump, if you push this each other, then it's also you will not be saved because velocity of their movement is so small. Everybody understand puzzle? It's not puzzle. It's our level of our knowledge, whether we know or we don't know, we care or don't care. It's also in this way. So, answer is extremely small, and we will if you are not ready to answer now, I am moving forward because it will be ready.
Well, yes, I'd like to.
Now, I know. That's I have to take into account this fact because it's a suffering. It's something with. Yes, please.
It's not the speed of the electrons in the wire that counts, it's the speed of propagation of the.
Sorry.
It's not the speed of the electrons that counts in the wire, it's the speed of the propagation of the field.
Where? Where? Correct, where? 3-2? That's there we are. That's where we are. Okay, I will satisfy your curiosity, and then maybe I will return tomorrow. We will approach this part. We should approach, because we don't have a lot of time. Electromagnetic energy never propagates through wire. It's very clever field. It's very clever. It does not want to go through wire. It goes through air. It goes, I promise, I will explain. I will explain. I have to explain, only remind me. Now only without formulas, without even vectors. So energy goes out, and it's ready to spread in all directions, in all directions. But wire has the purpose, only one purpose. It forces energy to travel along wire but outside. We will speak about charges. Here charges play fundamental role. So let us even solve this problem, because current goes in this way. So magnetic field perpendicular, vector pointing, there is such clever vector which shows direction of electromagnetic energy, density of propagation of electromagnetic energy. Then here, electrical charges arise. And this electrical charge creates normal component electrical field. You remember I wrote formula. Here current, magnetic field of the current perpendicular. Pointing vector which shows direction of movement of energy, always perpendicular E and B. So it goes along wire. Wire does not plays only one role. It's a guide which tells energy, go along, don't go in all directions. Then also there is a small, so when energy arrives here, not pumping as you told, then current starts to move. Current charges are moving due to energy which propagates around the wire. When you come to loading it's a very resistive material. Therefore, we will discuss about it. If I forget, please remind me. In resistive material, electrical field is large. Normal component relatively small. A vector pointing will be directed into. It's a very interesting subject, but I gave you only as example. I don't want to discuss, we jump too far away, but only question about velocity of ions, about conductivity. Velocity is extremely small. In pores, in rocks, even smaller. So let me leave it, otherwise I'm more than happy to discuss it, because I do believe it's seldom discussed even in classical textbooks, and that creates impression that through wire energy is going. Wire plays positive and negative role, which you look. Because wire is conductive, part of energy goes into and transforms into heat, and we lose it. So you see a lot of interesting subjects in our beautiful profession, a lot. I am already 40 years, I never tired to be surprised and enjoy to share with you. So that's about velocity of particles, about conductivity. You ask me about the resistivity of the rocks. Rocks, if it's not massive ore body, have conductivity due to ions, due to solutions. What is the resistivity of clay? Rocks, clay, approximately. That's what we have to know. Students, engineers, we have to know that, and we could be wrong 2-3 times. It depends on many factors, but It's nonsense to say clay has resistivity 100 ohmmeters. That's not fair. But if we speak about few ohmmeters, 10 ohmmeters, it means we have feeling about rocks. If we speak about sand, careful, sand could be dry, could be wet. It could have high mineralization, low mineralization, so resistivity changes widely, from few ohmmeters to 100 ohmmeters. When we are talking about limestone and dolomite, again, how many pores, what is the fraction, what is the structure of the pores, porosity, etc., etc. So I do advise you, it's not subject of my course, but I do advise you to have feeling. It's our laboratory, it's our place where we are working. We must know. Now, just a second. Now I would like to discuss back to Ohm's law. It's our current density, our third phenomenon, and Ohm's law. We have medium. Rho 1, Rho 2, Rho 3. We have electrical field at each point, current density at each point. Let us already answer a couple questions. What creates what? What my experience tells me, write down diagrams showing what is the cause, what is the result, and it's very, very useful, especially when we will come to electromagnetic fields. How we have to pick charges. I don't tell you where these charges. I mentioned, but I didn't want to discuss now. Charges always create what? Based on our complicated equations, electrical field. So always write next arrow tells yourself, if I have electrical field, it's caused by charges. Then, if I have current, it means charges which are moving. So, current happens due to electrical field. So, this is the sequence of events. Charge creates electrical field creates current. If non-conducting medium, only electrical field. Now, that's Coulomb's law, that's Ohm's law. Now, next step. Where are these charges arise, which are responsible for electrical field? Let us discuss. First of all, if it's an Earth surface, I placed now no more clouds. Let us make very clear weather. Now that floor is Earth surface. I took charge. Does it create current in conducting medium? So 10 million coulombs, huge charge. I went to Institute of Nuclear Physics, borrowed huge generator, created due to friction, for instance, huge charge, placed here. That's my Earth surface. Question: does this charge create current in the Earth or no? Sorry? That's my question. Maybe I didn't formulate clear. Does this charge create electrical field inside? Oh, I'm sorry. It's influence of lunch. So does this charge, which 1 meter above grass, so you have to visualize picture, Earth surface. I took huge electrical charge, and my question is, does this huge 10 million coulombs, I would like to increase take, so does it create electrical field in the beneath Earth? Suppose it does. Therefore, it creates what? Current. But you claim that charges which located above do create electrical field current beneath. But what was the first phenomenon which I tried to explain? First, we discussed the third now.
The electrical field within the body being reduced.
Sorry?
Electrical field within the body.
So, shortly, correct. First phenomenon which we can, now we are going to apply them. We are approaching slowly to physics. Now, regard no more clouds. I simply lifted 1 meter or half meter or 10 centimeters, huge charge, great value, great, 10 million coulombs. What we learn? This, according to phenomenon of electrostatic induction, all charges which are above Earth in free space, in air, what they are doing? They induce their electrical field, induce surface charges in such clever way that what? Inside total electrical field due to primary due to this charge plus secondary due to the surface charges is equal inside 0. So let us remember this fundamental fact. That's physics. And your geophysicists must be worried about it. Should be worried. Even we are saved. So all charges, regardless what is their value, if they are above Earth's surface, they don't create electrical field inside. And therefore our devices don't feel them. Each charge do create electrical field inside, but automatically they create what? Surface charges, and together affect 0. We are lucky, simply lucky. Now let us move forward. Where are these charges? Where do I'm talking about all electrical methods. Schlumberger profiling, soundings, Musala mass, normal probe, gradient probe, if you heard about it, lateral logs, all possible devices without any exception. So question is, I do have electrical field, but where these charges which create electrical field? And it turns out they are located at all interfaces. Understandable? Now, in order to get answer, let me speak about third physical last and third physical law which defines the behavior of currents in conducting medium. First law is coulombs, second ohms, and there is last third. It's not too bad to know physical laws and then feel comfortable. If I get results which contradicts one of these physical laws, I am wrong. It's a very good approach. So, current density describes current, and there is one physical law which characterizes distribution of this current. Who knows? Beautiful law. It's valid as Coulomb's law, as Ohm's law, even better as concerns Ohm law. You know? Huh? Sorry? Biot-Savart? No, Biot-Savart we didn't come yet. It's magnetics. It's another country. It's another author. So let us speak about, we have second field, and there is fundamental principle of charge conservation. What is it? As Coulomb's law, it's not derived from other law. It's a principle. It tells if you take inside of the medium any surface closed, inside of the rocks, this integral is equal to 0. What is it? And why it's called principle of charge conservation? Let us think together. Let me mentally imagine surface. First of all, no way for me to take surface in this room. Why? Because no current. It is insulator, air. But let me take closed surface inside first layer for it. Current flow, current density J. Let us consider this integral. What does it show? What does it show? Let me take one surface, ds. Let me take another surface, ds. Everybody understands what does vector ds mean? Area times unit vector. Let me take J, current density. Who can explain me what is the dot product, J ds? What is the physical meaning? I don't care about mathematical meaning. It's clear, dot product. But what does it show? Clearly as much as possible. Huh? That's mathematical approach. I would like to, you remember express meaning of current density. Sorry? But the first word I didn't grasp. Current, not current. What current density is? That's what I force you to think. Current density, don't tell a normal companion, tangential. Think what is behind of it. It's a number of charges, amount of charges. So what is now? I help you? Can you help me? What is a J ds means for any arbitrary surface? Amount of charges which are going through this surface per unit time. Correct? Now, can be this number negative, positive, can be equal to 0. Who knows greatly mathematics? Can be this quantity J ds positive. But now time T, not integral. I'm asking only about J ds, not integral. So I have part of surface ds. So when it's positive? When angle less than 90 degrees, then this product is positive. Why? Because dot product vector A times vector B equal AB magnitude, they're positive, times cosine between A and B. Clear? So when charge is moving from inside to out, we have positive contribution. When charges goes into negative, or when it's 0, perpendicular. So what is written here? Now I help you, again try to help me, and then I will help you. So what is written here? Always, without any exception, amount of charges which arrives into volume is equal, leaves. That's the iron rule. In no exception, not at all, never. That's fundamental physical law of describing behavior of the current. Why it's called principle of charge conservation? Stretch. Why it's called principle of charge conservation?
Because you're not destroying or creating charge.
Exactly. If you had inside of volume 1 coulomb before, then amount of charges which arrived equal amount of charges which left. Coulomb remains. If you didn't have charge there, you will not have. Now, as usually, physical law we write in 3 forms. If you remember, before lunch. First form, principle of charge conservation in straightforward form. Now, if I take small surface and divide by volume, what we will get? From previous hours. So integral through closed surface divide by small, divide by volume. Huh? How we call this quantity? Divergence. So another form of this physical law, divergence J equals 0. And there is another last form which is vital. I have interface. From this equation follows that normal component of current density must be equal. Let us, for curiosity, assume they are not equal. What would happen? So that's interface between our body and formation or overburden. Suppose normal component from one side is not equal normal component from another side. What does it mean physically? Huh? Exactly. Amount of charges which arrives to point would not be equal. What would happen in this case? Charge starts accumulate. If charge accumulates, changes with time, according to Coulomb's law, what would happen? Electrical field also will change with time. But we're dealing only with constant electrical field today. So, in order to provide constant electrical field, constant, at each point in our lovely conducting medium, normal components from both sides must be equal. If during 1 second they are not equal, you will have change of charge. So that's last and third physical law which we need in order to understand electrical methods. Now, back to our question, where charges arise. Again, we will do it without any derivations. Theory shows electrical methods. Charges arise only at interfaces. No charges inside. So let us take electrode A, electrode B, current flows, current density J, electrical field, and I state no charges inside. Is it fair or not fair to say it? So I claim sources of electrical field which we use in all electrical methods arise only at interfaces, but no charges inside. Does it sound strange? Strange. Circuit. Only please imagine battery. There is current through wire, 1 ampere. Ampermeter shows 1 ampere. Do we have charges inside? Take piece of copper wire. Take piece of copper wire, put insert ampermeter, and you will measure. If you have battery closed circuit, I promise you, ampermeter will measure and show you half ampere at least. What does it mean there is a current? There is a charges. But I claim density of charges inside of wire is 0. Could you help me to resolve this paradox? Sorry? No, just a second. Here air, free space. So I claim there is a current, but density of charges inside is equal to 0. Can you help me to?
Stay on the surface, put it one.
Sorry?
On the surface, and like the air and wire interface.
Oh, you think current goes on the surface? That's thank you very much. Thank you very much. It will help us to resolve another problem. So, I'm sorry, I would like to ask a different question. Thank you, you helped me to generate another question. When we have a current through wire in laboratory, where currents are moving, on the surface or inside? That's what we are going to discuss, correct? Okay, so?
Inside.
Huh? Inside. So you see, inside. Now let me ask you a question. I have wire, cross-section S. How current density is distributed over cross-section? For instance, one scenario, maximum current near surface. Another scenario, maximum current in the middle. There is a third scenario, uniformly. Current density could have the same direction. What is your feeling? On the surface. So, are there other suggestions? I deeply appreciate incorrect answers. They are extremely important because it's not examination. I came through different material. I would like sincerely to help you. Peter, it's already time because I'm listening. Now, it's very important, both types of answers, especially incorrect. Especially incorrect, because that's the basis for communication. So one suggestion is when you put battery created circuit, current goes on the surface. I know from which place this wind is created. I know. But it will be later, far, much later. So are there other suggestions? You have the same, at least you thought in the same direction, correct? That would be greatly help to resolve this paradox where there is no charges inside. Are there other suggestions?
It could still be in the center of the body following a sort of parabolic function.
So that suggestion, that's good. Are there other suggestions? So you see, we are far away from electrical methods. We are digging in a classical, simple example. But that's vital. If you would like to learn, you are young, and ask yourself take simple cases which you see every day around and answer. Are there other suggestions? So no.
Didn't you tell us before that the current actually from the transmission line from Sydney to Perth, you had it flowing in the air? No, the energy was transmitted in the air.
Energy, not current, energy. Now, but I'm talking about simple experiment which I don't believe one of you were able to avoid when you took course in physics or electrotechnics. You have simple battery, wire, voltmeter, ampere meter, resistance, that's it. And constant current. And usually circuit is made from wire which has constant cross-section, correct? Take from coil wire, it always has cross-section. It's not our geophysics, it's electrotechnic, much simpler. So, are there other suggestions? Uniform. And that's all. That's the simplest, always the simplest answer comes in the end. That's the rule of our life. So, yes, and the end. Now, so current, of course, if you have piece of wire, charges moving car in such way that vector current density is the same. What is behind of your suggestion is you are thinking somewhere you heard about skin effect. And skin effect by definition, it means current on the surface. But it happens with extremely special case, electromagnetic field and a relatively high frequency. So that's what happens. So back to my question. How would it happen that there is a current, there is a motion of charges, but I claim density of charge is equal to 0? It's very simple. Let me help you. You didn't have battery. Sorry? Let us make agreement about definition. What does it mean, electrostatic? But when we say electrostatic, it's a good, very good definition, but what is it? Sorry? It's correct, but it's a special case. Electrostatic, what? Static. Static, it means static in mechanics. No motion. So there is a static, there is a constant electrical field which implies that in conducting medium there is a motion of current with current density which does not change with time. So electrostatic is extremely very special case which does not have relation to electrical matter. Let us speak about constant electrical field. So let me explain what would happen. I don't have battery. What do you think? What would be the charge inside of piece of wire? Why 0? Why? Are there electrons there? No current at all. Piece of wire without motion, no battery, nothing. Do we have electrons inside of metal? Do we have positive charges inside of? What is the total amount of each piece of wire if you don't do something special? There is equal amount of positive and negative inside. And total charge inside, total, equal 0. Therefore, this charge does not create electrical field. Negative create electrical field. Negative. And positive, equal amount. So electrical field inside and outside due to these charges is 0. Clear? Now is it clear? Now, the same in the rocks. You came to the field, you didn't put your current electrode, didn't connect with battery, you have a lot of pores. Inside of the pores you have positive ions, negative ions. Total amount usually 0. I don't advise to, if there is no self-potential effect, etc., diffusion, your result is 0. Now, I connected back to wire, the simplest case. I connected by battery. What happens? What your physical intuition tells you? Positive charges don't move. Negative starts to move. What happens with total charge inside? I am talking about constant electrical field. You understand me, my question? So before circuit is open, piece of wire, you agreed, equal amount positive, negative charges. Now I turn on battery, turn on battery. So my electrons, they are very dynamic, they're moving slowly, very slowly, but they are moving. What happens with total charge inside of each element of the volume? How many charges negative arrive, so many negative leaves, and total charge is 0. So that's the same story in the rocks. Inside of each layer you have motion of charges, but total charge, positive, negative, inside of each volume is 0. Therefore, these moving charges don't create electrical field, and we are lucky. It would be disaster for electrical methods. But so we know charges above Earth don't create electrical field. Charges inside, they are moving, but total charge, positive, negative, 0. Where are these bloody charges which do create electrical field? Where they arise? At interface. So that theory tells at each interface, we will stop, at each interface charges arise with density. Let me write this expression, we will stop here. Constant ρ2 minus ρ1 divide ρ2 plus ρ1 times average value of normal component at this point. So if there is normal component above, beneath their difference, we know that's average value of them. So at each point of the surface, these charges arise with such density. Clear? Where we have interfaces between air and soil. Where we have else? When we put ground electrode between metal and soil. Where we have also between interfaces. Where we have also, especially, our body and surrounding medium. From this moment we will start up the break. So let us continue. Using three physical laws, Coulomb's law, principle of charge conservation, and Ohm's law, it's possible to show that at each interface, without any exception, each interface between media with different resistivities, surface charges arise. And these charges do create electrical field. They are responsible for our measurements. And these charges arise with density. Let me write it again, because I promised to write again. So 2 epsilon naught, that's not important, but rest is very important. It's vital. K12 times En average at the same point. So if it's a point P, in vicinity of this point, surface charge arises, which is equal constant, very important electrical method coefficient, which has name contrast coefficient, and times average value of normal electrical field. And now I will work around this equation, where K12 is equal ρ2 minus ρ1, ρ2 plus ρ1, or, since I need it, I will present in the following lovely form. And let us discuss it. It will be examples, and then we approach the first time to some very fundamental problems of electroprospecting. So, first of all, this is not equation which allows to calculate density of charges. Otherwise, it would be used after it Coulomb's law, and we don't need anything else. No. It tells only relationship between density of charge and normal component electrical field. What creates this field? These charges. So again, closed circuit problem. You would like to know charges. Sorry, you have to know field. According to Coulomb's law, in order to know field, you have to know these charges. So it's not an equation which can be used to calculate. That's first comment. Second comment, that's vitally important. In electromagnetic methods, we have several methods where charges play very important role. For instance, control source MT, where we measure very often effect due to charges. In VLF, we very often these charges play important role. There are other methods. So what I would like to say, this equation remains valid for all alternating field with electromagnetic methods except radar and some logging tools. But time domain, in frequency methods, in logging, control source MT, magnetotelluric, this equation is important for understanding, and I will tell about it later. That's two comments. So one comment, it's not equation for calculation, it only tells where these charges arise. Second, it can be used, it's used for electromagnetic methods. Now, let us read this equation. That's important. There is interesting coefficient, K12. It has name contrast, as I told, contrast coefficient. It's if you don't know physics but know mathematics of Schlumberger soundings or profiling, you always find in most books this coefficient K12. Let us so it plays very important role. It tells density of charges depends on this coefficient, and field, which in own turn depends on this coefficient. So let us look in this equation. How this coefficient depends on ρ2 and ρ1. Very important question. Very important. When I published with my teacher and my one colleague in 55 of this century, of course, this century, book about choice of frequency and electromagnetic methods, we use this example in order to show electromagnetic methods better than DC methods. But it was only 40 years ago. That was my first paper. So let us discuss this coefficient. I like to discuss this coefficient because it does not require any complicated equation, but it allows to remember something very essential. If I ask you how this coefficient and therefore density of charges depends on ρ2, what you would tell me? Strongly or not strongly? You understand my question? Huh? So the question is, what I'm worried, what my main concern, it should be yours concern, it's not too bad to have this concern. In all methods, seismic, gravity, magnetic, electrical, we would like to measure quantities which would be sensitive to change of parameters which we would like to determine. What we would like to determine in electrical matter? Resistivity and nothing else. Nothing else. We don't feel the electrical constant, we don't feel magnetic permeability, only resistivity. So if, for instance, my density of charge strongly depends on resistivity, good, then electrical field caused by this charge also, according to Coulomb's law, will be sensitive. And vice versa, it would be not very good if my charges would depend on resistivity in a very weak manner. So, back to my question. How this coefficient and ultimately density of charges depends on ρ2 and ρ1 based on this expression, strongly or weakly? Huh? Suppose you are right.
It's both on the contrast and the magnitude.
Would you be so kind to clarify your question? So let me take ρ2 over ρ1, 5. What would be the value of this coefficient? 5 minus 1. 4 divided by 6, so 0.8. Let me take ratio 100. So drastical change. What happens with this lovely coefficient? Don't forget, I changed 20 times resistivity. What happens with this coefficient? Huh? Almost 1. So, in one case, contrast was 5, another case 100. But this coefficient is almost either 0.8 or 1, very weak, depend. Therefore, density also depends very weakly. Therefore, electrical field which we measure also weakly. Let us remember about it, because this simple formula is not designed to calculate field, but it beautifully shows some problems with resolution, with geological noise and useful signal in all electrical methods, especially mining perspective. And we will discuss it, of course. So, now I would like to show you several examples in order you would try to remember what I did. So I told you it's formula valid for electromagnetic fields, please remember. Then, according to this formula, I almost forgot to tell you one thing, but now I will not miss. Suppose electrical field is such at this point that it has only tangential component. What happens with density of charges? Not too bad to remember. Not to remember. That's question how to put your profile, a long strike or perpendicular to the strike. That's very serious question. That's answer. So each time, if electrical field, for some strange reasons, tangential to interface, you will not create charges, and therefore you will not create what? Electrical field. Clear? Now, after this comment, several examples. I will start from simple cases. That's physics of electrical methods. Now, simple array, simple model, battery, ampermeter, B. I don't care now about measurements. There is a current, uniform half space. Help me, please. What happens here? You put two electrodes into ground, connected with wire. There is a current, 1 ampere. Current goes through wire. Then what would happen here? What would happen? So current from electrode will go into medium. I like it. But I would like to know where if I have here current, Therefore, I have to what here? Can charge move without electrical force? So I have to ask myself, what creates this electrical field? You follow me? So you have current. Charge at this point cannot move ion if there is no electrical force at this point. Positive ions will go in this direction, negative opposite. Question, where are these charges which create electrical field? Now, example number one, the simplest, no way to make simply, I promise you. Huh? In this case, no. There is another. In general, you are right, but I would like to specify place at the interface and the earth surface. What is the place? Electrode. That's the role of electrode. When you put here electrode, instantly at this interface, charges arise. Even it's known what is the value of the charge. Here positive charge equals to epsilon naught rho 1 I. What is the rho 1? Resistivity. What is the I? Current. What is the charge here? Minus 2 epsilon naught rho 1 I. But these two charges create electrical field. You see how simple if you understand physics. Current moving, here charges arise. Now, what is the electrical field along interface due to these charges? Tell me, please. But at this point, what do you see? Plane, you put two charges. What will be the direction of electrical field? Interface. That's so. That's air. That's two charges. According to Coulomb's law, how electrical field will be directed? It is just alone. So that it means in this direction. No normal companion. That's here, not vice versa. Thank you. Now, example number 2. Please remember what I told. Very interesting example. It will help you to understand. Earth surface, dike. Clear? Beautiful dike. Resistivity 10 minus 4 ohmmeters. Here resistivity 100 ohmmeters. So strike perpendicular to the black bolt. Clear? And it goes along for mile. For very strange, so it's a beautiful conductor. Depth 10 meters. Let me ask you a question. Suppose for very strange reasons, we were able to create primary electrical field, clear primary, caused by current electrodes, which one located 10 miles in this direction, another 10 miles opposite, A and B. What would be direction of primary electrical field? Along strike. Everybody understands? Along strike. E naught, what's caused by these charges. Now, beautiful conductor, beautiful. Primary electrical field along strike. Question. I put a man perpendicular to the strike, a man. Start to measure. What I will measure? Nothing. Nothing. Why? Because our primary electrical field is directed along of the strike. And according our equation, density of charges is proportional to total electrical field or normal component. Normal. So that's the reason why here will be very strong current. Why? Because primary electrical field everywhere, inside primary electrical field, outside primary electrical field. There is no secondary electrical field, no charges, no secondary field. Since conductivity is very high, flux of current will be huge. But measuring voltage with a man, you will get 0. You will miss your dike. Of course, it's extreme case, but it's designed to emphasize how it's important to create these charges. That's our goal, to create these strong charges in order to see target. Now, let me do opposite example. Not opposite, but different example. Now I am traveling perpendicular to the strike. A, M, and B. Tell me please. Now primary electrical field has this direction. Therefore, we will get strong normal component. And therefore, we will measure here. We'll have negative charges, another side positive, because rho 2, rho 1, in one case more and less. So we will get some signal. That's one of the iron rules in profiling. If you would like to detect using direct current methods, dike, go in profiles which are perpendicular to the strike. Physics, I hope you understand now this physics. That's second example. Now let us discuss third example. 4 body. Rho 1, rho 2. I put current electrode A, electrode B somewhere else. Don't worry about it. Now, I would like to detect this conductor. Let us, we don't need any calculations. Before calculations, we have to understand physics. First of all, how formulate correctly what is going on. Step number 1, here electrode, we have here charges, correct? Now, this charge creates electrical field everywhere. In particular, at points of interface. Therefore, at each point, we will have what? Charges. Now, here rho 2 less than rho 1, here we will have negative rho 2 less than rho negative charges. From another side, positive charges. That's what our voltmeter is doing. It measures voltage which caused by these charges. In effect, we measure 2 fields. We measure electrical field, primary, which we don't want, but we are forced to measure. Why we don't want? Because it's caused by charges in soil. It's our enemy. And plus secondary field, that's which contains information about light. So, using Coulomb's law, if we know these charges, we even can visualize direction of electrical field. Above, beneath, at all points. Now, that's physics of mining prospecting. Now, very important question. Now, the first time, not the last, I will discuss with you resolution ratio between useful signal and noise. Suppose we have a gain surrounding medium 100 ohmmeters, and we have 2 targets, almost the same dimension, and the same depth, the same shape, but small difference. This target, let us say 10 ohmmeters, some cavity filled by clay or salt water, doesn't matter. And then very good conductor, 0.001 ohmmeter. I am sorry, rho 2 and rho 2. Clear? I am sorry, these 2 targets don't look like similar. But that's I didn't notice. But let us try to do it in order to remove misunderstanding. So here rho 2.001 ohmmeters. Here 10 ohmmeters. Is the strong difference between resistivities? Very strong. Now I perform profiling. A, M, and B. One of the goals of all electrical methods, electromagnetics and mining prospecting, is distinguish between good conductor and poor conductor. As you know better than I, especially in Australia, geological environment, mining deposit is not far away from simple one. We have many sources of geological noise, and we have to have methods which better resolve anomalies caused by poor conductor and good conductor. Nothing else in effect in our electrical method. So now I would like to write expression which I wrote 2 times before. Now, I perform measurements. I got anomaly about this body. Clear? It must be because there are charges, they create electrical field. I'm moving my array. Understandable? Perform profiling. Without changing parameters, I move. So, yes, we will detect it. Let us assume detect it. But question is, what would be difference between anomalies above this target and relatively conductive and over target which is much more conductive? 3 orders, no, 4 orders, resistivities.
Much different.
Huh? How much different? They will be, huh?
Not very much.
No, for instance. So let us take some isometric body, not necessarily isometric, some pocket, very good conductor. You understand my question? Everybody understands? Everybody understands how it's important in our profession to be able to distinguish good and poor conductors. If all conductors, regardless of contrast resistivities, will create the same anomaly, usually we would be in deep, deep trouble. We will not know where to drill. So we very much would like to distinguish them, to have anomalies which would be different. So my question is, so one suggestion is difference anomalies will be very small. How small?
Then on the contrast.
I gave parameters already. I gave 100 ohmmeters surrounding medium. Here 10 ohmmeters. Here 10 minus 3. Difference ratio between resistivities 4 orders. Answer was given you a little earlier. Even I wrote equation. Let us read together. What is coefficient of contrast? Density of charges is proportional, not rho 1, not rho 2, but what? In this case, what would be coefficient K12? So 9, 11. Correct? So around 0.8, 9. True? What would be the coefficient contrast in this case? Almost 1. So is there difference between coefficient of contrast above or in these two cases? No. Therefore, density of charges will be practically the same. Therefore, voltage which you measure according to Coulomb's law, electrical field, at this point will be here and here. The same array, the same amount, everything the same. Will be the same. So, it's unpleasant situation. Very unpleasant, but that's reality. Usually, since I went through electrical methods directly after Second War, practically 55, 54, I know history. Of course, inductive electromagnetic methods were introduced first of all in the areas in Sweden, for instance, in Canada, where it's extremely resistive environment. Canadian shield, Scandinavian shield, where it's very difficult to put electrodes. Because these all methods were invented much early Second War, much early. That was good technical reason for introducing electromagnetic methods. First of all, frequency methods. However, there is another reason, much more important, or at least in the same way important, to deal properly, only properly, with electromagnetic methods. Under certain conditions, choosing proper frequency or proper time of measurement, it's possible much better to distinguish anomalies caused by completely different targets between geological noise and useful signal. That useful signal, that geological noise. So one of the most important principal, fundamental reason transition from DC methods in mining prospecting to inductive methods, frequency and time domain, is to improve ratio between useful signal and noise. Of course, we will discuss it at length. That's the most important. There is a technical reason, without any doubt, but in Australia we don't have shield. In many areas of the world we don't have Scandinavian or Canadian shield. We have opposite. We have beautiful contact with overburden, with all this stuff, and then this is the most important factor which in many cases makes frequency and time domain methods much better. Clear? Clear? Good. Let me show you another situation. You have noise, you have your useful signal. Resistive, relatively resistive. Again, 10 nanometers, here very conductive. What do we measure here? We measure total signal caused by this target, both targets, both in homogeneities, both bodies. One is our enemy, geological noise. That's useful signal. We measure both of them. Since density of charges is practically the same, what you can predict, which signal will be stronger? So voltage is equal voltage due to noise and voltage due to target. Noise, because density of charge is the same, but it's closer. So according to Coulomb's law, you will not see your target. So two cases, this case and second case, are designed to emphasize this ideal. Without any doubt, there are cases when direct current are useful for detecting dikes, conducting dikes, resistive dikes, no doubt. But they usually have much higher level of noise than electromagnetic methods. And in effect, since I touched this question, in effect, history of developing electrical methods for mining prospecting, it's a history developing methods designed to reduce geological noise. There are three stages: DC methods, frequency methods, and time domain methods. And I hope I will show you how moving from one stage to another stage, in many cases, in favorable conditions, we greatly improve ratio between useful signal and noise. In other words, we increase depth investigation. We reduce number of fault drillings, etc., etc., etc. Now, let me look what I have to tell you more about. I plan tomorrow. We have now a break. When we have a break, our break, tell me please.
5 minutes.
Huh? 5 minutes, very good. Now, very good. Just a second. You still don't ask me questions in spite of we don't discuss about curly divergence. It's very bad. Now, let me explain you what we measure in all electrical methods. So next question is concept of resistance and apparent resistivity. Electrode A, electrode M, electrode N, electrode B. So we created current. Always we measure two quantities. We measure current, ampere meter, and we measure voltage. Now, I introduced, so we created electrical field, there is a current field, so it's very convenient to use concept of potential. But now it's extremely useful. We can mentally imagine surface which is perpendicular to electrical field. How we call this surface? Who knows? Equipotential surface. Since electrical field perpendicular, there is no change of potential along. If you remember, I wrote you once today, derivative, if this component is equal 0, therefore derivative 0, potential does not change. So, what we are doing, our voltage V Mn equal Un minus Un equal. That's concept of voltage potential. We measure this voltage, divide by current. Each time, no exception at all. Two measurements, voltage by voltmeter and current in current line. How we call this quantity? Resistance. So there is no exception in logging, in a surface. We always measure resistance between two equipotential surfaces which are going through electrons. So when you are in the field, and measure current in line AB and voltage in Mn, and then divide, you determine resistance of this medium. Let me give you 2 minutes more, 2 minutes. Let us give you a few examples which we should know as geophysicists. Did you heard about logging, electrical logging? Can you give me examples of tools in logging?
An electrical array?
Electrical logging, not...
Free array or...
Huh?
The different arrays you use for points.
I see. So let me discuss with you briefly a illustration of this concept. We are talking in the same time about mining and oil logging. How this tool is called? I have to know what you don't know. Do you know this tool? Did you see this probe? Pole. So it's interesting. So let me show you something. Just a second. One of the most popular tools in all logging industry is normal probe, normal or potential probe. Since I will do it after break, but now let me tell you. Most of you involved, I'm talking about engineer in mining perspective. But electrical methods mainly are used in logging. 30% of all logging industry are electrical methods. Take these giants, Schlumberger, Western Art, Halliburton, and many dozen largest companies. It's a multi-billion dollars industry. and 40% of all well logging tools are electrical tools. Among of them, normal probe, gradient probe, lateral log, induction probe, and other modifications. So it's the largest area of application. 30% is going to nuclear methods. 30% goes to acoustics method and others. So that's the area where at least third of all logging well service is electrical method. So I will illustrate concept resistance using logging methods. And rest, please.
After